Right, so welcome back to our data structures class. Today actually we will be implementing the actual data structure using of course C++, which we've been learning. Well, most of the basics we have already covered already. So linked list, it used to be the most, how should I say, most important data structure in older days. I would say these days maybe it's not as important anymore as arrays in general. Oftentimes when linked lists have some specific properties, for as far as complexity goes, some things you can do very quickly, but in real life maybe you can sort of like delay going to a linked list solution. Just a basic array might be fine actually, right? But the main thing of course is that linked lists will offer you constant time insertion deletion. Let's look at the big old cheat sheet. If you look at linked list, why would you want to actually learn about it, right? Is that singly linked list insertion deletion is in constant time. So a linked list will be something you will want to learn if you need to add or delete a lot of items, right? Quite a lot. You're doing a lot of adding and deletion, and then later maybe, right, you can move on to array or maybe something else. But for now, right, you would want something once you're working on something, right? You want this inserting and deleting items, right? You want this constant time performance. Again, underneath, how are you going to implement it, right? There are different ways of implementing linked lists, actually, right? So, but for now, let's look at the theory a little bit, right? And then maybe also in the class we will do also some practical work on this, creating this this structure. Okay, and again, historically it's based on pointers, of course, so that's why it is kind of can get really messy if you do this by yourself. Of course, again, it's good for learning, that's why we are here, but in real life, again, you would probably use an existing implementation, right? But of course, you are job interviews, they want you to make a linked list, and well, you'll have to make it. You can't say, okay, I'm just going to use a built-in, right? They want to see if you actually know what it does, right? So we'll learn some iterators, right? We'll create some ordered linked lists, unordered lists, right? Also, we'll see about doubly linked lists. What improvements did they bring over regularly singly linked lists, right? So what's the thing with array? Our regular C-type array, well, has some. It's our basic building block. Array is like the most important one, right? Because you have a block of memory. But a classical C array, of course, array size is fixed. Well, we could be using vectors. That's completely fine, right? But the thing is, if you have unsorted array, you have to search for searching for something is slow. Also, the problem with arrays is if you want to include something, insert some data in the middle of it, well, you need to push all the data around. So it's for arrays, it's extremely simple to add data at the end, right? You just reallocate more memory, right? It's pretty simple to build some sort of like a stack type of structure out of arrays, right? But if you need to insert something in the middle or in the beginning, right? Especially in the beginning, in many languages, right? If you have a vector type of data structure, so you take a vector, right? Inserting items in the beginning of a vector will be very expensive because you have to push the whole data around, right? There's no ways around it, basically. You're using a big block of memory, right? You have a big block of memory, and maybe again, I'll fire up my paint, right? My trusty paint. So I have this big block of memory, right? Array, right? Array, right? So if I want to insert something here, right? This is green right here, right? A new something here, new item, you know, then I need to move everything here to here, right? So expensive, right? When I say expensive, it means linear time, expensive. I can't type, expensive. But you get the idea, right? Insertion, right? You have an array, right? So a big block of memory, you need to move it. So that's the basic what linked lists avoided. But again, like with everything with data structures and algorithms, nothing is free, right? You pay for this by some search and access will be very expensive for singly linked lists and also for doubly linked lists. So you can't win them all, basically. That's one of the takeaways from all of this course, actually, right? So you win somewhere, you lose somewhere. So here's an idea. So linked list is a collection of items. We call them nodes, and they will have two components. Singly linked list will have two components. Data, right? It could be anything. It could be an object, could be multiple attributes, right? Some data, basically, right? And you need address to the next same item. So that's basic idea. That is the basic idea, right? You have data and link, data link, right? So it's kind of really cool structure. Again, very nifty. So here's what it looks like, right? So you have a head, right? You have a pointer. You have a reference to something, right? To the first item, head, right? Otherwise you don't know where to start, right? And you keep going until you have reached what? You reach a null pointer, right? You reach end. Some sort of tail, some sort of, well, it doesn't have to be null pointer, it could be some sort of other sentinel value, something that designates that you have reached the end of it, right? So kind of cool structure. So why is this cool? Because you can insert at any place, assuming you know where to insert, right? You don't need to move the other items, right? We'll see about this insertion, right? So, yeah, so how do you do this, by the way? So notice this part here. So here's a trick, right? In some language, like most, I think Rust is really hard to do this in Rust, for example, right? So notice this part here. We have a pointer to the same data type, right? And this is legal, right? It's allowed, right? It just says, okay, yeah, we are defining a data type which includes a reference to itself. It doesn't have to be yourself. It doesn't have to be the same item, obviously, right? It could be a null pointer, it could be some other, usually it will be some other node, right? So you say a node, you declare a head pointer, right? So link component is a pointer somewhere in memory, right? So again, you could use, again, in C you use structure, but of course here you can use class or structure, but again, you use structure because it fits better, because it's public, right? We'll need this information probably, right? So that's like the basic building block. So something like this, right? So you have a head, right? Has a value, but also has a link. So these will be memory addresses. I guess these are these 28, 2000, 2800, 1500, 3600, right? So yeah, location. So this is this what's the color of this? What this called? What brown? No. Orange? Does this look orange to you?
Yellow.
Yellow? Come on, you guys, magenta, no, what's the color? Who has good color sense? Right. This is blue. Okay, we'll go with blue, right? But this is what color? I don't know. We got to look up a, but I'll call it the orange, brownish, yellow, right? Color, right? Those are memory addresses, right? Just some fake addresses. The book makes up some fake addresses, right? And they don't always care. It goes down. It doesn't have to be sequential. That's a key idea, basically, because, well, especially in all this, right? Memory expensive, right? You don't want to be, especially moving stuff around in memory is expensive, right? So it's nicer just you take what's available, right? Whenever you can create a new insert some new data, right? You take whatever the allocator will give you, malloc will give you. Right? So, again, so you keep going until you reach, of course, here you have, yes, question?
But the name of the color is ochre.
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 How do you spell it?
O-C-H-R-E.
O-C-H-R-E. Ochre. Ochre, I think, Latvian. I think. Ochre. Let me see, let's see. How do you find out? You had the enter.
Well, I asked co-pilot.
Okay. Ochre? Color? This?
Yes.
Yeah. Yeah, that's it. Very good, very good. Yeah. Deep orange, brown, right? It's like earthen color, right? CC7722 for those who want the hex values, right? Okay, so now we know, right? I've seen this color before, but of course It depends on the monitor, right? This looks kind of yellow here, right, to me? Yeah. But here in on my monitor, it's kind of, yeah, you see different color, slightly different. Yeah. Okay. Now with that out of the way, right, we can get to the topic at hand, right? So, current head, right? So, typically, right, again, if we are going, we'll want to go through some data, right? We'll need a pointer to where we are, right? So, of course, walking through or iterating is going to be the same speed as going through an array, right? Because you always know where to go next, right? So that's not very interesting, right? You just have copy, start at head, and keep going, right? So keep going to the end, right? Makes sense so far, right? Now you keep going. You update the current with the current link, right? So you keep updating the memory address where you should go next if you are iterating through this. That's the idea. Now, right, so we need to define a linked list. What do you need to do with the linked list? Right, so as we see from the cheat sheet, right, typically search, insertion, deletion will be what we want, right? So we search for something, right, matching some condition, like whether it's like includes, you know, Valdis or RBS or 5000 or whatever, something, some data inside, right? So that's search, right? So we'll need, of course, a way of traversal. Right? And with traversal, we already kind of know, right? We just keep looking for the next until we reach the end, right? So that's the idea. And then we get to the interesting part, right? Traversal is kind of, well, pretty much straightforward. Insertion, deletion will be the tricky parts, right? Which can give you sometimes headaches, but hopefully not, right? So traverse is just while there's not a null pointer, you keep going and do something, right? Current head, while current is not null pointer, right? You keep outputting the output, and of course you could store it and find it. So this is going to be what complexity? Traverse a linked list. What complexity? ON, right? It's a linear because you have to go through all of them, right? Traversal by itself, right? There's no extra complexity. I mean, I think all of them, right? You do ON, right? It doesn't matter, right? Because you can't skip, right? You can't skip any values, right? You don't know what's next. You just keep going. But this is the interesting part, right? So this is the tricky part, and then hopefully we'll have time in class to actually do it. So, how would you insert something, right? And this maybe hopefully have the this has actually some slides have this. So we have a new node with 50, right? And we have some info in there, right? We have 50 data, just some data. We want to store 50 in there, right? But we want to store it after this pointer 65, right? So how do we do it? We create this new node, and it's an orphan at the moment. It has no parent, has nothing, right? At the moment here, this line here. We store some data in it, and then it's the tricky part starts here, right? So where to go next, right? We know that where we are inserting, right? This 50 goes here, right? Node will go to where the previous, this part here, right? Maybe I'll show it to you here. Maybe I can draw. I think I can draw it here, right? Yeah, I can draw it. I think I can draw it. So, and the slides will show you also. I think the slides will show you. Yeah, slides will show you. So yeah. So this is the tricky part. So it's orphan at the moment, right? And that's where we're going to be inserting, right? So, well, this is with 2 pointers basically, right? We include where to go next, right? It's Q, right? Which is basically this part here, basically, right? We could use PQ, right? And then, of course, we update this one, the 65, the next address, the pointer is to wherever this new item is, right? So this is where it's all one operation. It doesn't matter whether our chain is million items long or 5 billion. So very efficient if you are doing this insertion. So I did this yet. You have to work with some data, but you know the order, right? Well, basically, yeah, if you know where you're going to be inserting, obviously this is going to be easy. The only issue with this approach, of course, is that, well, you need to have a pointer to the right place. And how do you find the right pointer? Of course, it could be a linear operation, like in the middle of somewhere, right? So it wouldn't really matter much, right? That's like you have some skipping, some pointers. Of course, you have a head in the beginning, it will be very, very efficient, right? So, again, if you know specific areas where you're going to be inserting, obviously, if you have some pointers, then, well, it will be very, very efficient. All one operation, assuming you know where to insert it, right? So, how about deletion? Again, you know 34 has to be deleted, right? This one here, right? So what we do is simply, first of all, we know how to know the address of this. So we basically, deletion is almost easier. Basically, we say, okay, the 65, basically, we sort of overturn it, right? But the problem is this, okay, this is all good, right? So the linked list is good, but the issue is this is, again, orphaned, right? It's still pointing there. So it could be potentially doing what? Memory leaking memory, right? If you're not deleting this, you need to free up the memory. So manual work, right? When you gain for this, again, this is going to be, assuming you know what to delete, right? It will be fixed all one operation. But the issue with this, of course, is that if you can just have this, okay, I know where this 34 is, right? But if you only have a singly linked list, well, how would you go back? Well, you don't know where it came from, right? You don't have a pointer to your parent. You only know where to go next, right? Then you have to, of course, know where you came from, right? Yeah. So again, so that's so linked lists are very good provided you know which items you are deleting, right? If you don't know, if you have to find them, it's still going to be a linear access, right? So, right, memory. So this part here, this 34 is dangling. It's hanging in the air somewhere, floating around, right? And that means we need to delete it, right? So this means typically delete, right? In C++ we'll use delete on, right? So we need to keep this pointer, right, and delete. So that before we update the links, right, we update the links. So we need some temporary pointers. And again, so that's the issue. If you have to do this by hand, it's easy to mess up the order, and you end up with data memory leaks all over the place, right? So that's the issue. But otherwise, I think it's not so hard, right? So deleting, right? We need to have two pointers. So Q, right? Q is going to be the link, right? And this is going to be deleting 34, right? We update the link for this to the new one, to this one here, and then we can safely delete the Q. So we'll see how it goes when we try to do it ourselves. Right. So how would we build a sort linked list? Well, we can build it backwards or forwards, right? So basically, we keep two pointers at the head, and also I would say tail would be also a good pointer, right? So then we have a very easy insertion in the beginning or at the end, right? Let's take a look how it would work, right? So we'll need three pointers. First node, right? Last node, and one to create a new one, right? Again, you don't need to, if you're always going to be inserting at the beginning, you don't need, of course, the end, right? So let's see, you have some data, right? And how would we insert? So we have first and last, typically first and last, or head or tail, right? And notice here, so we have two pointers, right? They're not pointing anywhere. We're going to insert it, right? So first, last, and, well, new node, right? And of course has no pointer here to nothing, right? So then we will do, right? Insert 15, right? We want to do first, right? First and last, but we are going to update. This last will move on to 15, right? Because we adding 15 at the end, right? And of course the number 2, which was previously, right? Previously was 2, right? 2 is pointing to the 15, right? And so on until we reach this type of, So first points 2, insert 8, 24, 34, and last node, right? And of course this is null pointer here, right? So again, so these the ochre colors, right? There's some memory address. We don't really need to worry what exactly it is, right? But of course we need to know where it is, basically, right? So yeah, it's very efficient if you know exactly where to insert. But the issue with this problem is why this is not so maybe not as crucial as before. You on all days, of course, memory is expensive. You need memory. You allocate it. These days, with caching, with computer architecture, arrays sometimes, even though it's technically not as efficient, you still use array to move things around. So that's the thing here, because we're jumping around. We are moving locality of memory addresses, right? Is whatever the memory allocator gives us. All right. So how about going backwards? Right? We could probably do, if you're doing backwards, you just need a pointer to the head, right? Yeah, because you're going backwards, so we'll keep pushing. You don't have to worry about the tail technically, right? So we start first, right? Null pointer, right? New node, and insert before first, right? Update volume, a pointer to first. Okay, so that leads us to building an abstract data type, and basically define what we want to do, right? Initialize, which should be a constructor, right? Empty, again, not all of those are required, right? Printing the list, which might be helping, right? Find the length also, destroy, and of course we want search, right? Basic, but we also want insert and the insert and remove, right? Insert, delete, right? Maybe a copy if you want, that's right. Insert and delete, right? So not all of these are required, but we'll see if we can get to implementing most of them. Right. So sorted and unsorted lists, of course, right? So obviously we'll just do a basic linked list, right? Unordered, right? So linked list type, right? We will create one like this. Abstract type, right? So build list forward, build list backward, insert two functions, insert first, insert last. This is extra work. We'll see if we can do this. So let's get started, right? And first, of course, we will need a node, right? Typically, we will use a structure, right? Because it's public, right? Easier to work. So let's go here, and I will start the code lab, code space, sorry. Okay, but yeah, so we will actually, the book wants us to go already abstract, right? So we are basically saying, right? I guess maybe I'll start with the regular one, right? Basically that we're storing some info, right? On just generic data type will follow, basically, right? So, but maybe I'll start with the regular. Let's start with the integer version first, right? We decide we are going to store some data. We'll start with that. Maybe easier a little bit, right? So linked list, right? CPP. Let's implement a simple linked list. Or node struct will store integer data and a pointer to the next node, right? Yeah, store pointer. It will or add node. Print the list. What else? And we will want delete node. I think that's basic it. And we will want also or linked list will have method to reverse node to find node list by its data, right? And that would be probably it for now. Like a really simple example, like a most basic one. That's all you really need, basically, right? The rest we can figure out later. Include IO stream using namespace standard, right? And so that's a definition. So this node, right? Again, in this particular case, so we decide, so we will be storing integers in our linked list, right? And this is the memory address, stores the memory address of the next node in the list. Could be null pointer, right? So far so good, right? And now we define a class. Now let's define a linked list. No, I'll do class. Yeah, I'll do class. Control D. Control D. Oh, I can do a Control D. Control D. Class. Again. Class. Linked list. And we'll have some private and public properties. So yeah. So let's take a look. Node pointer to the first node list. Again, so where it is, right? It could be private. We have public initializer originally, so constructor, so default constructor starts. Yeah. So basically, we have no meaning our list is empty, right? We don't have to allocate memory. So now, so far so good, right? Public constructor head to null. So null, actually, I think it's called a null. Well, let's use C++ pointers, null pointer. C plus null pointer, I think null pointer, right? Let's use this one, right? This C plus 111, right? So we should, this is, of course, doesn't really matter. Null is fine. Is a C, it's, of course, right? Expands, right? It's usually could be 0, of course, right? But this would be better, right? Do we need this one? Where is it part of? I think it's built in. Let's do null pointer, right? So null pointer. Pointer, no, right? I think this should be better. Yeah, that's better. That's C++ style. Right. Right, so that's constructor. So how do we add? So now it gets tricky. So this is a part. So by allocating memory first. So this is a part, right? New node, right? We allocate memory, right? We have some data, right? Because we're passing in through some data, right? And next is null, right? Again, I'll keep using null pointer because it doesn't really matter here, but I will use null pointer. Yeah. To be more C++ style. Still the same thing. So, how do we add? First we create it, we add the data, and we now, of course, well, to the end of the list, right? To the end of the list. Let's see if this works. Right? How will this work? Add node, append, right? Well, right, so now the problem, of course, is this approach, right? What AI is supporting. What's bad about this approach? Who can tell me what I don't like about this approach? This is AI code, right? Look at this here, right? Well, current head. So basically, right? If it's head, right, it's easy, right? Beginning is no point. So we start, right? New node. However, this part here is ugly because this is linear complexity. This is O(n) time, right? Not optimal, right? Again, we can improve it on it, right? We'll check if it works and then see if we can improve on it, right? So add at end, append, right? Append, node end. I'll call it end, right? We'll refactor it in a moment. So print list, printing list, of course, is very simple. Current next, we just print the data. Deletion, right? So we need to know, find the data, where it is, right? And notice this part here. We keep checking again null pointers. We get rid of null pointers. No, yeah, the null pointer. Yeah. All these null. All right. So delete data again. All right. Linear complexity. Worst case. In the worst case, right? Because we don't know where we are, right? So we just need, we have some data, we want to delete it, and of course we will delete the node. The first instance will delete the first instance of the node with data passed in. So yeah, if there's like 5 instances which have 9,000, we'll delete the first 9,000 node, right? The other 4 will remain, right? You have to keep deleting them, right? So not optimal at all right now, right? The node is found deleted, right? So here we find it, we delete. So if current is not null pointer, right? And if previous equals null pointer, then of course head is current next, right? On else previous next, current next. We update, and we can then safely update the current node, right? We keep looking, right? And if we find it, basically, right, we can safely update it. Now, what else? We will need probably finding something. But we want to return a node. So notice this is going to return a pointer to the node. And again, this is, well, this here is, this will be linear by definition. Yeah, ON, right? Not really, we can't really improve it right now. So let's try to see if this, let's see this in action. Let's see this linked list in action. Int main, right? And I will do this, I could, I guess, pass argument count and see how this does it, right? So this will work. Print list, delete 3, right? Print list again. And we'll find, right? Node found, node not found. Okay, and exit success. Okay, let's take a look. So G++, sorry, G++, and we'll take a break in a moment. G plus, vol, come on, linked list, output, L list, list. Okay, so you see it found, right? And of course, if it's not null pointer, right, we know the data found, right? And of course, node not found is, so everything is good, but we will probably want to improve on this, right? So I will save this option. First implementation of linked list, right? But there's plenty to things to do, right? So again, so this, what I don't like is this part here, this especially adding to the end, right? How about adding to beginning, at beginning, right? Let's add this one. Let's add a method. I think we can do this. We have a couple of minutes. Let's add method to add to the beginning. Let's think about how this would work, right? Add node beginning there. So notice this part here. Compare this here. You have to traverse, right? Here we make a new node. We have data. It's dangling at the moment, right? And then we simply say new node next is head, and head is new node. This is elegant. This is beautiful, basically, right? So this is where the O1. This will be O1. This will be O1 operation. What we want, right? So this part here, at the moment is dangling. at this moment new node is dangling. Yeah. Now we connect it, right? And of course, crucially, we say, okay, this is a new node. Again, if we forgot to do this, right, then we would not have a way of getting to it, right? Right. Head is a new node, right? Because we will lose the address otherwise, right? If we did not set head, the new node, we would not know how to find the new node, right? So this is of course optimal, right? Optimal way of working. What can we, so we're doing so well, assuming everybody is able to follow, right? So this add node at the beginning makes sense? Or
Again?
adding node at the beginning, this part here, how we added.
Yeah.
Yeah. So we add some data, of course, to it, right? And set the next pointer to the new node, the current head. Okay. Again, we would like to probably make this abstract and make it generic, meaning using templates, right? You know, not all we don't know what kind of data we want to store in this linked list, right? We probably want to have not only integers, maybe we have some strings, maybe we have some objects, maybe of some type class, maybe we want to store cars, or I don't know, cities or students, and so on and so on and so on, right? So we can make this generic. We'll probably do this after the break, but we could get started. Let's try to make this very generic, but it'll make our code slightly, I guess, a little bit trickier, right? Let's take a look, right? And I guess I could make it a separate file. But let's add head. So if you want it at the end, right, you probably want a pointer to the tail. Tail would be helpful, right? It doesn't cost us, right? So, well, I'll be using it. Thank you, AI. I want to use it. Don't say what I don't want to do, right? I will be using it. Tail. Yeah. Okay. So, how we do initialize? So what changes? We have like, oh yeah, you have to leave, right? Yeah. So yeah, we'll take a break in about a minute or so. Right. So I'll see you on Thursday. Okay. Good. All right. So I do tail. Right. Makes sense. But now we have extra work, right? Because tail pointer is going to be moving. So when do we have when is tail going to change? Well, when we add node at the beginning, right? A new node is head, right? At beginning, well, do we need to check right now if head is a new node? That's correct. Now, if tail is null pointer, right? Should we update this tail? I think we need to update, right? If we add the beginning, it kind of makes, you know, if inserting, well, obviously in the beginning, if you had the beginning, right, then it would be, tail would also need to be updated, right? Also, yeah, so basically this part here, right? If, come on, let's do it. Yeah, so we gain this, so it's always this a little extra check. If tail is null pointer, if tail new node, right? We always have to do it, unfortunately. If you're adding it, right? We just check, right? Tail also needs to be updated. Head, easy. Tail needs to be updated. So how about end? We'll do this after the break, right? So we'll improve it, right? To do, I'll add to do. To do, make adding to the end O1, right? So that's what we'll do after the break. So we'll continue at 12:10. 12:10. All right.